And the same expression can be found for the magnetic field. Now let's see what this propagation constant is. Gamma is the so-called propagation constant. And it depends on the nature of the medium where the wave propagates. Of course, free space or vacuum is one very particular situation. Let me give you the expression. Dimensions is meter to the minus 1. Let me now give you, okay, you know omega. Now, mu0 is the magnetic permeability. In our situations, we will always find a magnetic permeability that is pretty much that of vacuum. We will not discuss magnetic materials. So magnetic permeability is for P minus 10 Henry per meter. This is the expression for vacuum. And this will not change. Things that are going to change are epsilon and sigma. Now, epsilon is the dielectric constant. And this is defined as the product of epsilon 0 times epsilon r, where epsilon 0 is the dielectric constant of vacuum. It has got this number of farad per meter. Vacuum dielectric constant, absolute dielectric constant for vacuum. And epsilon r is the so-called relative dielectric constant. And for our medium, this is going to be always larger or equal to 1. Being equal to 1 in vacuum. There is a situation that we are not considering in this course, that is ionospheric propagation. If you propagate through the ionosphere is a plasma, and in that case the dielectric constant can be lower than 1. Actually can go down as 0. But this is a very special material that is we will not discuss in this course. As far as we are concerned, the dielectric constant is always larger or equal to 1. Relative dielectric constant. Now, sigma is the conductivity of the medium. Dimensions are Siemens per meter, or 1 divided meter per ohm, as you like it. This value is quite often 0, apart from particular cases that we're going to consider, like the ground, the terrain, or metallic objects. If a medium is not conductive, is not a conductor, then sigma is equal to 0. If it is a dielectric, then sigma is equal to 0. Now, you put everything into this equation, you calculate the square root of a complex number. Please make yourself familiar with the calculation of square roots of complex numbers. You may have a calculator that already does this. If it does not, it's very simple. But please, you will have to calculate the square root of complex numbers in this course. So, the square root of a complex number, iota is of course the imaginary unit. You get a real and an imaginary part in general. So there is a real part of the propagation constant, that is alpha, and an imaginary part of that constant, that is beta. Now, if you replace this quantity into that equation, you end up with I have just separated the real and imaginary parts. Now, this term here is, if present, is if alpha is larger than is not 0, then that negative exponential actually implies an attenuation, because this number goes to 0 for increasing values of z. That is, the amplitude of your electromagnetic wave, if alpha is not 0, decays exponentially when you propagate through the medium. And in fact, we will find that this alpha is larger than 0 for lossy media. And I shall discuss lossy media in a moment. For this reason, alpha is called the attenuation constant. And the dimensions is Neper per meter. Actually, please remember that Neper is non-dimensional. So actually, the actual dimensions of alpha is 1 divided by meter. This is a complex number, e to the minus iota beta z is a complex number whose absolute value is equal to 1. And the phase of this complex number delays for increasing values of z. So this is just a phase delay. Is a phase term. So beta is called phase constant. Now, if you do all the calculations, you find that beta is equal also to 2 pi divided by lambda. Lambda is the wavelength. I'm not doing the math, but it's easy to demonstrate. Lambda is the wavelength. And is defined as the speed of light in the medium that we are considering divided by the frequency. Please note that V must always be smaller or equal to the speed of light in a vacuum. So what happens is that you may have a medium, you calculate the properties. So when you have a medium, you have the values of the magnetic permeability, the dielectric constant, and the conductivity, if any. Once you have this, you can calculate alpha and beta, you applying this equation. Once you have beta, you can calculate the speed of light in that particular medium by doing the reverse of this. You calculate lambda, from lambda you calculate the speed of light. Two things. When you go from one medium to another medium, the frequency does not change, because the frequency is a time property. You need non-linear medium to change frequency. What changes moving from one medium to another one is the wavelength. In this equation, the frequency never changes. What changes is the speed of the wave in the medium, and hence the wavelength. So please do not change frequency when you go from vacuum to another medium. This also means that if you do the calculations and you calculate the speed of light in that medium, please verify that it is smaller or equal to the speed of light in vacuum. You can never ever, in our situation, find the values for speed larger than this number. If you find them, your calculations are wrong. Why I'm saying this? Yes, please.
How can a non-linear medium change the frequency of the wave?
Because if you have a non-linear medium, you have a non-linear relations, say, between electric field and magnetic field. So non-linear operations, if you take, for example, something that is and you square this because the medium is non-linear, for example, then you find that cos squared, and the cos squared has got two components of frequency, one of frequency 0 and one of frequency twice omega. So in principle, non-linear relations do change frequency. And actually you use non-linear relations in circuits to build frequency converters. How do you modulate a carrier? You made a product that is a non-linear operation, a product between carrier and a modulating signal. And what you end up is a modulating signal that is translated around the carrier. So that's a change in frequency. Or you multiply two sinusoids in a multiplier, and you get the difference and the sum of the two at the output. Non-linear medium are not frequent in nature, let's say. You need very particular materials, but you can find them. But this, of course, they are no interest for our mobile propagation. More questions? Okay. As I said, why I'm stressing this point that seems to be quite a minor point. I'm stressing this point because it happens to make errors in calculation. All of us, we all make computational errors. That's normal. This can happen also at the test. The kind of mistake that you make, better, the way I judge your error, the mistakes that you make, is different. What is important is not the mistake itself, but the way you react at your mistake. Let's assume that you do this calculation and you find that the speed of light that is larger than the speed of light in vacuum. The same mistake, if you write a note and say, okay, oh, I understand this is not possible because this is not physical. I've done somewhere a mistake. I have no time to check it. As far as I'm concerned, this is much, much less important as a mistake than writing nothing. If you just say nothing and you find something that is twice the speed of light in vacuum and you do not comment, you do not say this is clearly a mistake, then that particular error is much worse for you than the other one. Because you must have a physical sense of the things that since you are going to be engineer. So if you are asked to calculate the weight of a man, something that's not related to this, and you end up with 10 kilograms or 100 kilograms or 1 ton, you must be able to comment. If you get 1 ton, you should say, okay, this is clearly an error. If you say 1 ton and you do not comment, really means that you are not into the topic, okay? So even if you do mistakes, please write them, and you notice, because they are not physical, you got values larger than the speed of light in vacuum, you got efficiencies larger than 1, anything that is not clearly not physical, please write, because I will find them anyway, okay? I will find the errors anyway. But what is important is the way you handle your mistakes, okay? Because so I know that you have some physical understanding of the phenomenon. Of course, you cannot distinguish between 2.1 and 2.2. There is no way to say which is correct. So if it is not possible, it is not possible. Okay. We need one more piece of information here. Now, the power density is, in this particular case, is very simple to evaluate because is if you are in vacuum or and this is batch per square meter. What does this mean? This means that if you take 1 square meter so you take an area here that is 1 meter times 1 meter. This area is crossed by this power density. Across that area, this is 1 meter times 1 meter, you get this value of power. Now, in this also, at this point, it should be clear why the plane wave cannot exist. You can spot why this particular wave is not physical. what is the total power carried by this wave? Not the power density, not the power per square meter, the total power. It's infinite, of course, because if you sum up all the contribution on the xy plane, that's clearly infinite. The plane wave, by definition, extends from minus infinite to plus infinite on the x and y plane. So it's carrying a total power that is infinite. So there's no way to generate this. We shall be back on this soon. But first, let's talk about polarization. Now, the polarization of a wave is important because we can generate or we can receive, we can transmit or receive waves with a well-defined polarization. So when we design a radio communication system, we have to have polarization in mind. Unfortunately, the environment quite often changes the polarization of the wave that we transmitted. So it's playing tricks on us. And we have to be prepared to this. But first, of course, let's see what polarization is. For this discussion only, let's go back from the phasors domain to the time domain again. As I said, we have seen that we have two couples. Now let's consider the electric field only. So when we talk about wave polarization, we refer to only the electric field, because the magnetic field is, once the electric field is given, the magnetic field is given, because they are strictly related. So what is wave polarization? Wave polarization is a description of the behavior, and I will be clear on this. What I mean with behavior is a description of the behavior of the electric field on the transverse plane, of course. We know that. The behavior of the electric field on the transverse plane in time. That is, we want to know what the total electric field or the electric field of this wave is doing in time. We have to imagine to be able to look at the electric field, and we have to describe in words what that the electric field is doing with passing time on the xy plane. Okay, let's take a generic electric field. You know that the generic electric field can be decomposed into components. To be clearer, now I draw here the transverse plane, the xy plane. This is the total electric field. It is going to be function of the z and t. sphere, two components. And now let's write the expression in the time domain of those two projections. Of course, this is going to be, let's call this x, yes. We go back to the time domain from the Bezos domain. Plus an absolute phase difference. Phi is the phase difference between the x and the y component. There is an absolute constant phase difference phi. Let's call this phi0. Now, let's put ourselves on the xy plane, like shown here, means z equal to 0. We put ourselves on the transverse, exactly on the transverse plane. So these equations simplify like this. Since zeta is equal to 0, this beta zeta disappears. And this is what we have here. If this is actually the xy plane, z is equal to 0, we can take z equal to 0. Now, as I said, when we talk about wave polarization, we are telling what this total electric field is doing in time. We watch, like in a movie, what this electric field is doing on that plane. In particular, which geometrical figure is described in time by the electric field. That's the polarization. And let's start with some very specific cases. Case number 1. Phi0 equal to 0 or P and Ex and Ey absolutely arbitrary values. Okay, this is the first case what we see. If we force those conditions in this equation, what do we get? Let's start with 0, then I do the other case. But let's start with 0. We get, of course, those are the expression of the two components. Now, if we want to describe what is the total electric field is doing, what do we need? We need to know two things. First, we need to know the length of this vector, that is the absolute value of the total electric field in time, as a function of time, if any. And we have to know the orientation in space of the electric field. That is, we have to know what if the angle, the orientation in space of the total electric field changes or not in time. Okay, let's start from the absolute value. Now, the absolute value, let me calculate the square, it's easier. The two components are perpendicular to each other, so we can just square. So if we replace with the expression in here, we got so we end up with so the amplitude of this vector, if you look at the expression, is varying in time with the absolute value squared is valued with cosinus squared. So the absolute value is varying with cosinus of omega t. But what about the orientation in space? The orientation in space can be calculated by calculating this angle, C function of t. And if you look at the expression, it is simply the arcotangent of the y component divided by the x component. Now we can replace EY and EX with the expressions they have in our particular case, and we simplify we can simplify this like that. Now, which kind of polarization is this? As I said, when we talk about polarization, we are stating we want to describe in words what is the geometrical figure that the electric field describes in the plane. So what can we say about this polarization? The amplitude depends on time, yes. So it goes to 0 when cos omega t is 0 to a maximum value that is 1. So if you look at what happens in time, the amplitude of this vector goes from 0 to a maximum value. And what about the orientation in space? Does the orientation in space depends on time? Does the angle have any time dependence? No, because the time dependence cancelled out. So no time dependence. So we have a geometrical figure that is described by a vector whose dimension changes in time, but the orientation does not change in time. Which kind of figure, geometrical figure, is this? If you look at the electric field, what in time, you imagine you have a clock that is advancing, which kind of picture or figure this electric field is drawing on the blackboard? And that's what do you call that? A line. So the electric field will oscillate along the line, will not change direction, linear polarization. And what about the magnetic field? We do not specify anything about the magnetic field because the magnetic field is always perpendicular to the electric field and always in phase. So if the wave is propagating towards you, then the magnetic field is like this. Does not change direction because the electric field does not change direction. It's always perpendicular and it is perfectly in phase. Now I'll show you next time with my PC an animation of the electromagnetic wave. But when the electric field is maximum, the magnetic field is maximum. When the electric field is zero, the magnetic field is zero. Because the ratio between the electric field and the magnetic field is 377 ohm. So if this is zero, this must be zero. That's why we never discuss magnetic field in polarization. We talk about electric field and the magnetic field follows. Okay? What happened with this? Well, nothing special. You just have a change in sign here because you are going to end with something like this, and this is P. So all you got is a minus sign here. Actually, the minus sign is irrelevant in the amplitude. You got a minus sign here. What does this mean? This means simply that instead of oscillating in the first and third quadrants, your electric field is oscillating in the second and fourth quadrants. But it's always a linear polarization anyway. And this is one of the most popularly used polarization states in telecommunications. There is another one, but we have no time to discuss it today. We shall see it next time. That is non-linear polarization. I will not anticipate anything. But there is another one that is always very popular. Now, if you design a communication system, you build or you buy an antenna. The antenna, possibly, will generate an electromagnetic wave linearly polarized. If you want to receive the maximum available power at the receiver, you must use an antenna that is matched in polarization, that receives in linear polarization. We shall see this when we talk about antennas. So polarization mismatch is one of the most common causes of non-working radio links. Because unfortunately, nature changes the polarization state of your wave when it propagates through the environment. And you have to take this into account. Okay, questions? Yes, please.
You deal with vacuum
Almost always, yes, because the way that we are interested into propagating vacuum or the atmosphere. But we will find some values that are different from the vacuum impedance when we have interaction of waves with the lossy medium, like the ground or the building materials. In that particular case, you have to take into account that that's not vacuum. Yes, please.
When we change the angle, where will be the magnetic field?
The magnetic field will always be perpendicular, so the magnetic field is going to be like this. Because you always have to follow the right-hand rule. So E times the H in the direction of propagation. More questions? Okay.